Hi, everybody. I hope you guys are all doing well. This lecture video is on Chapter 3, Part 1, and Chapter 3 is acids and bases. Okay, so you'll recall, hopefully, from general chemistry that there are many definitions for an acid and base, but we're going to use the Bronsted-Lowry definitions primarily, just because that's the most useful definition for organic chemistry. For example, like Arrhenius's definition has to do with water, and since organic chemistry primarily does reactions in solutions other than water isn't organic, it can be more helpful to use a different definition of an acid or base. So we'll use two. We'll use Lewis acids and bases, and then Bronsted-Lowry acids and bases, with Bronsted-Lowry being the most common type of acid base that we'll discuss. And if you recall, the Bronsted-Lowry definitions for an acid is that it donates a proton and a base accepts a proton. So if we look at this classic example, of course, this is not it's not an organic reaction, but that's okay. We're just looking at a classic general chemistry example. We'll see that, for example, hydrochloric acid can be an acid, which will donate its proton to, for example, water, which can act as a base, and be a proton acceptor to form chloride and hydronium ion. So that's a classic example of an acid-base reaction that you've probably seen many times before. So given that, let's practice figuring out what the products would be if we have a couple of different reactions. Now, in this case, we're going to be looking at what would the products be if water acts as an acid in a reaction versus if water acted as a base in a reaction. And water is considered sort of neutral. It can be either an acid or a base, right? So it doesn't mean that it's neither. It just means that depending on what it's being reacted with, sometimes if it's reacted with something that's much more basic than it, it will act as an acid. And if it's reacted with something that's much more acidic than it, then it will act as a base. So it's sort of what we call amphoteric. It can go either way. So go ahead and take a minute and see if you can figure out what the products would be in the case where water acts as an acid versus a base. Okay, hopefully you took a moment to try to work on this problem. If not, we'll go ahead and go over it together right now. So if water acts as an acid, and again, we're using the Bronsted-Lowry definition, then it will be a proton donor, and the base will be a proton acceptor, right? So basically, we should be donating one of these protons, right, to the base. So we'll end up with the nitrogen making 4 bonds and an extra bond to hydrogen. And it does that, it will end up with a positive formal charge. And then we would also end up, if water acted as an acid, with a proton donor, so we end up with hydroxide. So note that the only thing that gets donated in a proton transfer is the proton. And why do we keep saying the word proton instead of hydrogen, right? Well, it's not that the hydrogen atom is being transferred, because recall, hydrogen atom is both the proton in the nucleus and the electron surrounding it in an orbital. The only thing that's getting donated is actually the nucleus of the hydrogen atom, not the electron that is currently being used to form the sigma bond to the oxygen atom. So actually both electrons in this bond are left behind on the acid, and that's how this oxygen gets 3 lone pairs and a formal negative charge. And the only thing that's transferred is just this nucleus, again, of a hydrogen atom. The electrons for the bond actually come from the base, specifically this lone pair on this base is being used to form a bond, right, with just the nucleus of that hydrogen atom. So when we say proton transfer, we kind of use that terminology because it's important to understand that we're only transferring hydrogen nucleus, right? Not any electrons associated with it. Okay, and then what if this is the acid? So if this was the acid, we would donate its proton, right, to water as the base. So this is donating its proton. Remember that it does not donate anything other than hydrogen's nucleus. So it leaves these electrons behind. We would end up with two lone pairs. And in this case, the nitrogen would have two lone pairs and a negative charge. And then the base accepts the proton and uses one of its lone pairs to form a bond with that proton. So we end up with hydronium ion. All right, moving on. Let's talk about using curved arrows in reactions. So you probably remember that in the last part of chapter 2, we used curved arrows quite a bit. But we use those to show electron movement in a series of unhybridized p orbitals in the concept of resonance, right? So resonance is not showing a true reaction. It's not showing a change in structure. The point of resonance structures is to show all the contributing line structures, right, to a hybrid or more true structure. So curved arrows, they're going to be used in the same way as chapter 2, but we're going to get to do more things with them because now we can show bonds breaking and forming, whereas we couldn't have shown a sigma bond breaking or forming in resonance, right? Because in resonance, we were only dealing with electrons in unhybridized p orbitals. But when we're breaking and forming sigma bonds, we're going to be showing the formation of bonds that use hybridized orbitals in lone pairs that potentially come from hybridized orbitals as well. Okay, so we can definitely show that electron movement with curved arrows, right? Recall that we're going to start an arrow tail on a source of electrons. That could be a lone pair. It also might be a sigma bond, right? Or it could be a pi bond. But in this case, we have a lone pair and a sigma bond. And then we point to where they're going. And that's a little bit more vague, but basically what this is showing is that this base is taking its lone pair and it's going to share those electrons with the hydrogen's nucleus to form a bond between the base and hydrogen's nucleus, which we show here. The electrons in the bond from what we're going to call A, which is the acid, and the hydrogen stay behind on the acid. And then we form two new species, right? And whereas we call these the base and the acid, on the right-hand side of the equation, we're going to call this the conjugate acid and conjugate base. Remember, those terms are used, right, to show the base on the right-hand side will be called the conjugate base. And that's basically the thing that would take the proton in the reverse reaction. And then the proton donor in the reverse reaction will be the conjugate acid. So let's look at a specific acid-base example that uses an organic substrate. So even organic substrates potentially have acidic protons, right? So we can show a proton transfer from an acid like acetic acid. So we can see here that the curved arrow is showing us that the base, which is hydroxide, specifically one of the lone pairs on the oxygen, is going to take the proton, right, from this hydrogen atom. The electrons will get left behind as a lone pair on this oxygen. And then that ends up with the negative charge moving from hydroxide to the conjugate base, which we actually call acetate ion. Okay, so when I've been talking about this, a lot of times organic chemists will say the base attacks the acid or attacks the proton. Of course, that's not really true. You know that molecules in solution are moving around, right? They're eventually might run into another molecule. And if they run into it with the right orientation in order to allow a reaction to occur, then a reaction occurs. So you can think of it as all these like ping pong balls moving around. And if they happen to collide, right, with the right orientation, there can be a reaction. So it's not like the base is a heat-seeking missile trying to find the proton, and it's the only one moving around, right? The acid and the base sort of move until there's a reaction. So just because we talk about molecules, sort of anthropomorphize them a little bit and say one attacks the other like there's intent, that's not really what's happening in solution. We want to make sure we understand the difference there. And then, of course, I want you to make sure you understand that when we draw a curved arrow with a, we call a double-sided hook here at the end, we are showing the movement of two electrons. So these two electrons are being used to form a bond, and then these two electrons in the bond are being used to form a lone pair. So it's the movement of pairs of electrons that's occurring here. Okay, so an important skill is to be able to identify which steps in what we call a mechanism. And a mechanism is just all the steps involved in getting from reactants to products. And a lot of times there's more than one, what we call step in a reaction to get from point A to point B. And some of those steps will be proton transfers, right? And so we call those acid-base steps. We want to be able to recognize which are proton transfers and which are not. Right? So for example, if we look at this first step, which is that this oxygen's lone pair is picking up this proton, and then these electrons are being left behind on the oxygen. This is a proton transfer. So step one is definitely a proton transfer or an acid-base step. The second step just involves one arrow. You can see it here. Basically, this sigma bond is breaking, and then two electrons are being given to the oxygen. And then this is sort of splitting apart into two different species, two different structures. So there is no transfer of a proton, right? Because remember that transfers of protons require two arrows. So this is sort of a dead giveaway with it's only one arrow, and we're not actually showing a base taking a proton from an acid. So step two is not a proton transfer. And we do have names for other steps, but we won't learn those until later in subsequent chapters. Okay. And then the last step here, we see there's an oxygen, this lone pair, right, is being used to pick up this proton. The electrons are being used actually to form a pi bond between these two carbons. And the reason it can do that is because right now this carbon has a formal positive charge. So it is deficient in electrons, right? It only has 6 electrons around it, and it wants to have 8. So it actually can accept 2 more electrons. So the electrons from this carbon-hydrogen bond can actually be used to form a secondary pi bond between these two carbons. And that's what this is showing. But because we have what's a base, right, a proton acceptor, taking a proton from a substrate where it's just donating its proton and it keeps its electrons, this step is a proton transfer step as well. Okay, so let's go on to section 3.3, which talks about quantifying acidity and basicity, and specifically starting with acidity. So you might remember from general chemistry, how do we quantify, or what's the difference between strong acids and bases compared to weak acids and bases? Maybe you can take a moment and think about, what do you know about strong acids or bases in comparison to, for example, weak acids or bases? So maybe you came up with the idea that strong acids or bases completely dissociate in solution, and weak acids only partially dissociate, right? Or and that's good. Maybe you actually quantified it a little bit and said, okay, well, strong acids have a large Ka, right? And weak acids have a smaller Ka. And you can talk about Kb as well. So those are all great things to remember from general chemistry, right? So it is important to understand, right, the strength of an acid or a base, because that will help us predict how a reaction will progress, right? For example, if it's a strong acid, it's very likely to react very well with even a weaker base, right? And vice versa, if it's a strong base, it could react even with a weaker acid. Whereas if you have a weak acid and a weak base together, there may not be a reaction. So let's remind ourselves, how do we use quantitative strength analysis using specifically pKa values to compare the strengths of acids, right? So we're definitely going to remind ourselves about pKa and how it relates to acid strength. And then talk about what happens if you don't know the pKa of a compound, right? Is there another way to analyze potential acid-base strength, especially like to compare between two things? And that we can rely on a qualitative strength analysis as well, if we don't know the pKa. And so we'll learn how to look at structures and figure out, right, based on some rules, what's likely to be more acidic than something else. Okay, so let's review starting with the quantitative strength analysis. So remember that how Ka is calculated. So it's an equilibrium constant for the reaction between acid and water. And specifically, it's the concentration of the products over the concentration of reactants. And recall that if you have a very large number, then that means that there was a lot more products than reactants at equilibrium. And we say that's associated with a strong acid because it more completely reacted. But Kas can also be very small numbers with negative coefficients. And that relates to a weak acid, right, which does not form products in solution. So Ka values actually range from 10 to the negative 50 to about 10 to the 10. And these sorts of super small and super large numbers can be difficult to imagine the difference between. So that's where pKa comes in. pKa is just a negative log of the Ka value, which basically allows you to focus on the exponent of the Ka value. And we end up with pKa's that range from negative 10 to 50. And so what we want to remember about pKa's is that the smaller the number or the more negative the number, it corresponds to a stronger acid, right? So a pKa of negative 10 is an extremely strong acid. And a pKa of 50 is a very weak acid, right? One of the weakest acids you can possibly have. So just remember, the smaller, right, the number, the stronger the acid. And some pKa values of some common acids, both inorganic acids like the first two and the third one, and then some organic acids as well, are listed in table 3.1. And it's important to note that each pKa unit represents an order of magnitude or a power of 10. So if I asked you, which is a stronger acid, sulfuric acid or hydrochloric acid, right? Most people would be able to say sulfuric acid, but by exactly how much, right? So we want to look at the difference in the pKa value, which is 2, right? So sulfuric acid is 10 to the 2 or 100 times stronger than hydrochloric acid. So just remember that each difference in 1 in a pKa corresponds to a power of 10 for strength, right, of the acid. And then the other thing to remember that's really, really important is the association with a strong acid and its corresponding conjugate base. So for example, if we look at again, sulfuric acid, which is a very strong acid, the conjugate base of sulfuric acid, which is formed when you remove one of its protons, is actually a very weak base, right? So there's an inverse correlation there, or an inverse relationship, excuse me, not correlation, between acid strength and base strength. The stronger the acid, the weaker the base, and vice versa. The weaker the acid, the stronger the conjugate base. So looking down here on the other end of the scale, right, we have a structure, ethane, right, where there's a hydrogen attached to a carbon atom that's being considered in terms of its pKa value. So the conjugate base would be to remove this proton, but it keeps the electron. So there's a lone pair here in the negative charge. So this ethane has a pKa of 50, right? So it's basically one of the weakest acids you can imagine. That means that its conjugate base is actually a very strong base, right? So make sure that you remember that relationship. That's super important. Okay, so if we have pKa values of both the acid and the conjugate acid in an acid-base reaction, such as for this example, right? The acid is acetic acid. We know the pKa of acetic acid is 4.75. The conjugate acid in this case is water, the pKa of which is 15.7. Right? So if we know the pKa of both the acid and the conjugate acid, we will be able to predict which direction the equilibrium will favor. And the equilibrium always favors the formation of the weaker acid, right? So water being the weaker acid, which is why the arrow is bigger here on top than in the bottom, right? So this is a very, a reaction that really proceeds, right, to products very well. But when we say very well, like how do we quantify that, right? Well, what we can do is think about the difference in the pKa values. Specifically, we can say the difference between the pKa value of 15.7 and 4.75. It's approximately 11, right? So what does that tell us? That means that there'll be 10 to the 11 more products than reactants. So if there's 10 to the 11 more products than reactants, then this is not much of an equilibrium, right? There, really, the forward reaction is happening, is much more favored than the reverse reaction. And in solution, we're primarily just going to have the products, or a large concentration of the products, and a very, very small concentration of the reactant. And in Klein, sometimes he says that, you know, a difference of 10 or more in terms of pKa units is essentially an irreversible reaction, or we treat it as it's an irreversible reaction. It doesn't really go back to reactants. So there's no, you know, significant concentration of reactants in solution. And, you know, in reality, if the reactants and products stay in solution, there's always an equilibrium, but we can essentially treat some reactions as if there's, you know, it's not reversible. Okay, let's talk about the qualitative perspective and trying to figure out, let's say we don't know pKa values, which would be more acidic by just analyzing the structure of two acids, right? So it basically, qualitative analysis allows us to compare the structure to determine which is a stronger base, right? Which then we can use to determine acid strength through that inverse relationship. And we can also really take advantage of the fact that most bases will have a negative formal charge, right? And we know that formal charge affects stability. If you have a very unstable formal charge, let's say that's localized or depending on what atom it's on, right, then it's going to be a stronger base than if you have a negative charge that's pretty stable, right? So formal charge can definitely affect the stability, and which will can tell us eventually which direction of equilibrium will favor, right? Because we always know that reactions favor forming the more stable thing, right? Could be the more stable acid or the more stable base, which we also say is the weaker acid or weaker base. Okay, so if we were using structural analysis to determine which of these two is a stronger acid, and you might be thinking, well, probably HCl, because we know that's really acidic, right? But that's neither here nor there. Sort of like, how do we know, right? What about the structure tells us that this might be the stronger acid? And so what you actually want to do when you're comparing two potential proton donors or acids is actually to compare the stability of the conjugate base. So when you're trying to figure out which is more acidic, right, by qualitative analysis, what I want you to do is actually not to consider the structure of the acids themselves, but consider the structure of the conjugate base of those acids. And in order to draw the conjugate base, we need to remove the proton, but leave the electrons in the bond behind. When we do that, we end up with chloride, right, versus, and in this case, if we remove this proton, but leave the electrons behind, this ends up with a carbon anion. So we can actually look at the structure of chloride versus this carbanion to help us figure out, right, which one of these is more stable. That will be the weaker base. The other one will be the stronger base, right? And let's say we figured out one was the stronger base, then it would have the corresponding weaker acid, right? So I'm not going to do it right now because we are going to be moving into slides that compare these two, right? But the goal of the next section is to compare the atom with which the negative charge and the formal negative charge and the lone pair are on for stability. We're going to figure out one is more stable than the other, right? So let's say I figured out this one's more stable, this one's less stable. The one that's more stable will be the weaker base. The one that's less stable will be the stronger base. And if we figured out this is the stronger base, that means the acid was a weaker acid. So that's going to be the sort of analysis that we're doing here. And I'm not giving away the answer to this one. I just want to show the sort of thinking that's going to be involved as we learn how to do this process. Okay. So when we are, not quantifying, but qualifying acidity, right, we're going to look at a series of factors that help us understand the stability of a negative formal charge. And the factors that we're going to be looking at are the type of atom that carries the charge, whether or not there's any resonance, induction, and also the type of orbital where the charge resides. So Klein puts these together and he came up with an acronym, which is ARIO, right? And the A stands for atom, and then resonance, right? And then I for induction, and O for orbital. So we're going to be using and remembering this acronym in order to be able to figure out how stable an atom is with a negative charge. Okay, so the first thing we're going to look at when we're analyzing using this acronym is we're going to look at the atom, right? And again, the atom stands for the type of atom that carries the charge, right? So for example, you saw before in our previous example, it was a chloride, right, or a chlorine atom, and versus a carbon atom with a negative charge, which we call a carbanion. So those are two different atoms, so we can definitely compare the atom for its ability to stabilize that negative charge that was on it. And what we know, probably from previous knowledge, hopefully, is that more electronegative atoms can better stabilize a negative charge. And we even really talked about this when we were looking at the significance of resonance structures. Recall sometimes we were comparing two structures where the only difference is where the negative charge resides. Is it on, for example, a carbon or an oxygen? And then we talked about the fact that an oxygen atom can better stabilize an extra electron and negative charge due to its enhanced electronegativity compared to carbon. So electronegativity is definitely an important factor here, right? And we know that atoms in the same row, right? If the atom is more electronegative, it can more effectively stabilize a negative charge. Let's go ahead and do an analysis between the acidity of butane and propanol to figure out which one we would predict to be more acidic. So remember, we talked about if we want to figure out which is predicted to be more acidic, what we need to do is compare not the structure of the acid, but the structure of the conjugate base. So for example, I'm going to draw in the conjugate base of butane and the conjugate base of propanol. Notice that we have a carbon, and feel free to draw in the C if you want. Remember, with line structures, we typically don't, but it's okay at this point if you're still drawing in C's for your carbon, right? So we have a carbon with a negative charge versus an oxygen with a negative charge. So if we're looking at atoms in the same row, what we'll see is that oxygen is more electronegative, right? So it's predicted to be able to stabilize the extra electron and negative charge more effectively, right? So we'll say this one should be more stable negative charge due to the enhanced electronegativity of oxygen versus carbon, right? So the important thing here, just the more stable part. Okay, so if it's more stable, think about it. Do we predict that to be the stronger base or the weaker base? So think energetically, right? I'm very stable, I'm low energy. If I'm very stable and low energy, am I likely to be really, really reactive, right? As a base, a strong base? No, right? I'm much more likely to be a weaker base because I'm already happy and stable, just like I am. I don't really need to pick up a proton, I'm already stable, right? Something that's very unstable, very high energy, can be a much stronger base because it needs that proton to become more stable since it's high energy and less stable to start with. Okay, so then the more stable base, right, will equal the weaker base. So then this is the weaker base, and this, by comparison, is the stronger base. Right, so now we have the important information here, right? And we can use that inverse relationship to go, okay, this is the stronger base, right? Is it predicted to be the weaker acid or the stronger acid? The stronger base corresponds to weaker acid, right? And weaker base correspond to stronger acid. So that is our qualitative prediction. And then if you use the pKa table in your book to actually look up the pKa, right, of these two, what you would see is that the pKa of butane is about 50, or it says of similar compounds. So it's about 50. And then pKa of alcohols, right, is typically going to be about 16, 17. So I'll say about 17. Okay. So this is definitely predicted to be the stronger acid. And the pKa value tells us that it's the stronger acid because it has a smaller pKa value. So going back to the slides for a minute, right? Recall that when we want to compare two potential acids and figure out which is a stronger acid, we compare the stability of the conjugate base. And then use that information to give us information about acid strength. Okay, now let's look at another example. And it says compare HF versus HCl versus HBr. And immediately, hopefully, you're thinking about, okay, if I'm going to compare those, what I'm really going to compare is the conjugate base of each of those, right? I'm not going to compare these directly. I'm going to compare the strength of the conjugate base. So really, right, I want to compare fluoride to chloride to bromide. Right, so we compare the stability of the conjugate base to then make predictions about the acid. Okay, so looking at these, right, where are these located on the periodic table, right? So they're actually in the same column in the halogens, right? And so it actually says, okay, before making any predictions, well, okay, let's say at this point, if you made predictions, right, a lot of students would say, okay, it's based on electronegativity, right? And the more electronegative atom should be more stable with the negative charge, right? So you would predict this is the more stable because fluoride is definitely the most electronegative atom. Okay, so then more stable, we would predict this to be the weaker base, and this is the stronger acid, right? That would be the analysis. If you were just looking at electronegativity, which I had taught you from the previous slide. But if we look at the pKa values, we see that the pKa of HF is 4. Then we have HCl is -7, and HBr is about -9. Okay, so what is this telling us, right? It's actually telling us that this is the stronger acid. If this is the stronger acid, this should be the weakest base. But the weakest base is the most stable. So why is bromine with a negative charge more stable than the more electronegative fluorine with a negative charge? And the answer has to do with the fact that electronegativity is the dominant factor when you're comparing atoms in the same row, right? But size is the dominant factor when you're comparing atoms of a different size, like those in the same column. So it's, even though this is the most electronegative element, right? What we know is that this is the largest element, right? And the larger elements, significantly larger elements, actually stabilize a negative charge more effectively than smaller elements. And that's just because the electron is in a bigger orbital, so it has more molecular freedom. And as a result, right, the size is actually a more important factor than electronegativity, right? So it's because this is the largest size atom, right? Again, not having anything to do with electronegativity, we say that it is the most stable anion, right? And again, most stable means the weakest base, which would make sense, right? Because the weakest base should correspond to the strongest acid, which is what we see when looking at pKa values. So when you're looking at the atom, remember that there's two factors. There's electronegativity and size. And it's really helpful when you're comparing carbon versus nitrogen versus oxygen versus fluorine to think about electronegativity. And then as you get larger, atoms are even more stable due to their large size. Okay, going back to the slides for a minute. We're now going to be doing a problem where we're asked to predict the equilibrium position. Right? So the question actually says, draw the curved arrows that lead to the conjugate acid and conjugate base. Right? Draw the products, label the acid base and conjugate acid and base. And then at the end, right, answer this question, does the reaction below favor reactants or products? So basically that equilibrium arrow, should we draw it favoring the products, going in the reverse direction and favoring the reactants? So if you can take a moment to pause the video, you can think about it on your own first, and then we can go over it. Okay, let's go ahead, go over it, assuming that you've already worked on it for a minute. So the first thing it said is to draw the curved arrows, right, that lead to the conjugate acid and base. So with the oxygen having a negative formal charge here, right, it's more likely to act as the base. And then they've drawn out this hydrogen attached to the carbon. So certainly looking like this is going to be the proton donor or the acid. Right? So then my arrow will start from one of the lone pairs on the base to show the formation of a bond, right, or picking up this proton, and the electrons being left behind on the acid to form the conjugate base. So then the products, if hydroxide picks up a proton, it becomes water. Go ahead and draw in water. And then the acid becomes the conjugate base, right? And we lose this proton and we end up with a lone pair and a negative charge on this carbon atom. So we have now the conjugate acid. So you might remember that the base forms the conjugate acid and the acid forms the conjugate base. Or the other way to think of it is in reverse, which one would be the proton acceptor and which one would be the proton donor. Right? The proton donor is always the acid going back to form these products, and the proton acceptor is always the base. So what would be the acid and the base if you were going in reverse direction to form these products? Okay, so I think we did the first part here. And now it says, does the reaction below favor the reactants or products, right? Basically what this is asking us is, right, should I draw this arrow or, right, should I draw the reverse? So which way does the reaction favor? That's the question here. How do we figure that out, right? So recall that when you're trying to figure out if, for example, if the acid or the conjugate acid is a stronger acid, we don't compare the structures of the acid. What we do is compare the structure of the base and the conjugate base and use that information to infer about acid strength. So if we're comparing then, right, so we compare, right, we're going to compare the base and conjugate base. And so what we're looking for is there a difference in the atom, right? And the answer is yes, right? This is an oxygen with a negative charge. And this is a carbon with a negative charge. There is a difference in the atom. And if we remember that periodic table, right, we know it's carbon, nitrogen, oxygen, fluorine, and increased electronegativity. Right, and oxygen is more stable with a negative charge because it's more electronegative. Right, so this one is predicted to be more stable, which means weaker base. Right, and then conversely, the carbon with a negative charge is less stable, right, which means stronger base. Okay. And then the equilibrium, right, will favor the formation of the weaker base. Think strong things, right, will react to form weaker, more stable things, right? So it's definitely likely to favor the weaker base. So based on that, we're gonna, oh my gosh, what I did down here. I didn't even realize that I basically drew the same thing and I was pointing in the same direction. Anyway, we want to go this direction. So weaker base, right? We're going to use this one. We're going to go point towards the weaker base. And you could have also done the analysis with the acid. It takes a few more steps, but you can definitely do that and say, okay, this is the weaker base, right? Then that means that this is the stronger acid. And then if this is the stronger base, this is the weaker acid, right? So stronger acid and weaker acid, equilibrium will favor the weaker acid. So you can either think of it as the equilibrium favors the weaker base or the weaker acid, depending on which one you're actually comparing. Okay. That should be enough information to get you through the first activity, today's activity. Good luck, and remember there is both a printable key and a video key if you get stuck in working on today's problems. And let me know, as always, if there's any questions.